Sorry, got interrupted there, but here we are. If K is about 1, that means we have a relatively decent mixture of reactants and products. Most of the time, K is going to be much greater than 1 or much less than 1. K isn't often very close to 1. All right. Let's look at some general rules for K, then we'll go through some examples. So we can work on these rules. General rules for equilibrium constant. First of all, it has no units. Even though when we look at our equilibrium constant expression here, yes, these are concentrations, so this is molarity. So one would think, wouldn't this be molarity squared divided by molarity to the 4th power? We're just like, we're not going to deal with that. With rate constants, yes, we dealt with it. With equilibrium constants, we're not going to deal with units. K has no units. All right. Things we do not put in the equilibrium constant expression are solvents. If something is dissolved in a solvent, the concentration of the solvent is not going to be involved in equilibrium constant expression. We do not put solids in there because what's the concentration of a solid if it's in a jar? If you have a 1-liter jar and you have a penny in it, what's the concentration of penny? Well, yeah, it doesn't make sense. All right, so we're not going to put solids in there. You don't put in pure liquids either. So no solvents, no solids, no pure liquids. Well, if you can't put in those three, what can you put in the equilibrium constant expression? Turns out anything that's gas or anything that's aqueous. Now, in this class, most of our solutions are going to be aqueous, where our solutes are going to be dissolved in water as our solvent. They'll be aqueous solutions. However, once you get to organic, we find you've got other solvents that will work. So it's just as long as your thing is dissolved in a solvent, then you include it. In this class, we're mainly going to see it as aqueous, meaning dissolved in water. And those are included in there. Okay. So let's go through some examples of writing equilibrium constant expressions. And I believe once you get the knack for it, you're going to find, well, this is not hard. All right, here's our reaction. 2NO gas plus O2 gas in equilibrium with 2NO2 gas. Everything's a gas, so everything gets put into the equilibrium constant expression. Recall the equilibrium constant expression is products over reactants. So K equals concentration of NO2 squared, because we've got the 2 right here, NO2 squared, divided by concentration of NO squared times the concentration of O2. Very straightforward. Let's look at this next reaction here. CH3COOH aqueous plus H2O liquid in equilibrium with H3O plus aqueous plus CH3OO minus aqueous. When we look at this, we realize, okay, aqueous, yeah, liquid. Nope, we do not include liquids in our expressions. Aqueous, okay. So the equilibrium constant expression would be the concentration of H3O plus times the concentration of CH3COO minus divided by the concentration of CH3COOH. We just do not include H2O. It's not in there. Okay, what about this one? AgCl solid plus when you put it in H2O, it goes to Ag plus aqueous plus Cl minus aqueous. Note, I put the H2O above the equilibrium arrows, meaning I just want you to know that I took solid silver chloride and dissolved it in water, tried to dissolve it in water. The water is not part of the reaction, I'm just dissolving this. So I put the H2O above the arrows, meaning it's not a reagent in the reaction. Well, what are we going to put in our expression here? Aqueous, aqueous, solid. Solids don't go in there. So K, our equilibrium constant, equals concentration of Ag plus times concentration of Cl minus divided by, well, what's it divided by? Well, there's nothing on the reactant side that goes in there, so we just put 1. So it's divided by 1. We don't have to write divided by 1. So, yeah, here, equilibrium constant is just the concentration of the 2 product ions. I hope in the future we get to look at that more in depth. Wouldn't that be fun? All right. Next one, NH3 gas plus H2O liquid in equilibrium with NH4OH. Well, aqueous, yep, goes in there. Liquids, no, water does not go in there. Gases, yes, that goes in there. So K, the equilibrium constant, equals concentration of NH4OH divided by the concentration of NH3. Okay, next one. P4 solid plus 6Cl2 gas goes to 4PCl3 liquid. Well, liquids don't go in there, gases do, solids don't go in there. So the only thing that'll be in here is our Cl2 gas, but note it's the reactant, and it's always products over reactants. Since no products go in there, we just put 1. And the equilibrium constant expression is K equals 1 divided by the concentration of Cl2 to the 6th power. Cool. All right. Well, let's look at some more relationships between the equilibrium constant and the chemical reaction. What if you can change up the reaction? How does that affect your equilibrium constant? All right, so let's take a look. First thing, if you have the reverse equation, if you reverse your reaction, you need to invert your equilibrium constant. The new equilibrium constant is 1 over the old constant. For example, here's the reaction. A plus 2B in equilibrium with 3C. I think by now we can all figure out that the equilibrium constant expression is K equals concentration of C cubed divided by the concentration of A to the first power times concentration of B to the second power. And I put a little F there, meaning this is the forward reaction. But what if we reverse the reaction? What if we wrote the reaction as 3C in equilibrium with A plus 2B? We just took this reaction and flipped it, made the 3C product the reactant, and made the A and B reactants the product. If we flip it over, the equilibrium constant expression for the reverse reaction would be products over reactants, concentration of A times concentration of B squared divided by concentration of C cubed. And you can see when we compare the forward and the reverse equilibrium constant, they are just the inverse of each other. So the reverse equilibrium constant equals 1 divided by the forward equilibrium constant, which means if you had a number for your forward equilibrium constant, if that number was, say, 1,000, the reverse equilibrium constant would be 1 divided by 1,000. Okay, what if you multiply your reaction? Say, up here we had A plus 2B in equilibrium with 3C. What if we multiplied that by 2? 2A plus 4B in equilibrium with 6C. What we can find, the equilibrium constant is just still the same. Products over reactants raise their stoichiometric power, but this is a 6, a 2, and a 3, whereas up here it was a 3, a 1, and a 2. What we realize is that is just our original equilibrium constant values squared, because concentration of C to the 3rd power squared is the concentration of C to the 6th power. Concentration of A to the 1st power squared is concentration of A to the 2nd power, and so on. Which means if I wrote this reaction, my equilibrium constant, the value, the numerical value for the equilibrium constant here, would be the square of this equilibrium constant value for when it was just 1 times all those. All right, another thing to look at, what if you add reactions? Recall Hess's law and all that good stuff, and this is also important when we get to mechanisms where you add elementary steps to get an overall reaction. If you can add reactions together to get an overall reaction, note the equilibrium constant for this first reaction would be the concentration of B squared over concentration of A. The equilibrium constant for the second reaction would be the concentration of C cubed divided by the concentration of B squared. Note that the equilibrium constant for this overall reaction, when we added these up, and you can cross out the 2 B's when we add these up, the overall would be the concentration of C cubed divided by the concentration of A. Note that you can get the concentration of C cubed divided by the concentration of A by taking K1, B squared over A, and multiplying it by K2, C cubed over B squared, which tells us the equilibrium constant for the overall reaction is just the equilibrium constants for each step multiplied by each other. So if I had a value for this and a value for that, I could calculate the overall equilibrium constant. Hey, wouldn't it be fun to do an example of that? Why, of course it would. So here we go. Here's a reaction. Set of reactions. H2CO3 aqueous is in equilibrium with H plus aqueous plus HCO3 minus aqueous, and we can calculate, we find that equilibrium constant to be 4.2 times 10 to the minus 7. Here, next reaction, HCO3 minus aqueous is in equilibrium with CO3 minus aqueous plus H plus aqueous. Equilibrium constant for this reaction, I'll call it reaction 2, is 4.8 times 10 to the minus 11. The question is, what is the overall reaction and what is the overall equilibrium constant? Unfortunately, this is very, very simple to do because we've done all of this before, just about. The overall reaction, well, we just add these two up. We get to cross out whatever appears the same on both sides, so cross out the 2 right there. And note our overall reaction is H2CO3 aqueous, and that's everything on the reactant side, is in equilibrium with 2 H pluses, aqueous, plus CO3 minus aqueous. Good old Hess's law here. And once we have that, what is the equilibrium constant for this overall reaction? Well, that's just going to be K1 times K2. It's just going to be 4.2 times 10 to the minus 7th times 4.8 times 10 to the minus 11th, a little calculator action, and we get 2.0 times 10 to the minus 17 as our equilibrium constant for that overall reaction. Yeah, it's not too difficult. I know you're pretty bummed by that. Don't worry, we're going to get into some difficult stuff later on. Okay, cool. So, the next section in your book discusses something, and we need to discuss it, and then we will not speak of it again. At least not too much. All right. When we look at our equilibrium constant expressions, when we're looking at all of our equilibrium constant expressions up here, these are always concentrations. And we always use molarity in our concentrations, mole per liter. And then someone had a brilliant idea. Well, it's an okay idea. And I said, wait a minute, but what if everything in your reaction is a gas? What if everything in your equilibrium constant expression are gases? Can we use the ideal gas law to do something with this? And you can. And they said you can actually calculate an equilibrium constant. Instead of using the concentration of everything in moles per liter, you can calculate an equilibrium constant just using pressure. If everything in your mixture, everything in your reaction is a gas, then you can use pressures and partial pressures and get an equilibrium constant using that. Okay, but note, often that equilibrium constant will be a little bit different than the equilibrium constant using concentrations. So what you will find in your book and in your notes a bit is we're going to look at Kc, which is the equilibrium constant when we're using molarity as our unit of concentration, and Kp when we're using pressures. And it turns out Kc and Kp are related. Because if you look at the ideal gas law, we know PV equals nRT, pressure times volume. Of course, volume is in liters in ideal gas law. N is the number of moles. So if I just took V over to the other side, divide both sides by V, I get pressure equals N over V times RT. Pressure in atmospheres equals moles per liter times RT, and moles per liter is molarity. Therefore, the ideal gas law rearranges to pressure equals molarity times RT. If you're using equilibrium constant expressions with concentration, you're just dealing with molarity. If you're dealing with pressures, it's molarity times RT. Now, R is a constant. And so as long as you know the temperature and you run the reaction at that, you can actually calculate what Kp is based off of the idea that Kp, the equilibrium constant related to pressure, is going to equal Kc, that deal with molarity, times RT to some value n, where n is going to depend on the stoichiometry. For example, if you have A plus 2B is in equilibrium with 3C, and all of these are gases, let's assume all three of these are gases, Kp would equal, well, if we're looking at pressure, it would just be the pressure times molarity times RT. So pressure of C is going to equal the concentration of C times RT, and that would be cubed, divided by the pressure of A, which would be the molarity of A times RT, times the pressure of B, which would be the molarity of B times RT, and that would be squared, since you have to square that. And note what we find out here is you have concentration of C divided by concentration of A divided by concentration of B, multiplied by the concentration of RT cubed, times divided by the concentration of RT times concentration of RT squared. Note all those RT cancel out. Because our stoichiometry cancels out here, we have 3 on this side and 2 plus 1 is 3 on this side. Kp actually equals Kc in this example. However, what if you had just A plus B goes to 3C? We have 3 on this side, 1 and 1, 2 on this side. We'd find out that Kp does not equal Kc. It is off by a factor of 1 RT. Now that we have gone through this, we are not going to be doing this math on exams. On an exam, I'm not going to ask you to, given Kp, calculate Kc, or given Kc, calculate Kp according to this reaction. I just want you to know that you can use pressures if everything's a gas, or you can use concentrations if it's not. Most of the time, the vast majority of the time when I am writing out these notes, I'm just going to use K. I'm just going to use K for the equilibrium constant. I always mean Kc. So if you just see a K written in there, is that Kp or Kc? Don't worry about it. It's Kc. It is concentrations, not pressures. I'm just not a fan of Kp. All right. Some people are. Some people get super, super jazzed about Kp. That's just not me. Okay, well, let's do some real math. Start getting in some good math now. Turns out there are two, well, actually, no, let's pause this video right now because this is getting a little long, and we'll get into some good math in the next video.